Hello, my name is Ryan Chard and I'm from Argonne National Laboratory and I'm presenting our work on a distributed, federated function-as-a-service platform called funcX. So this work is really motivated by there being a new class of data-intensive researcher. Advancements in instruments and detectors have seen an explosion in the rate and volume of data that can be generated by fairly typical laboratory equipment. These devices can easily generate gigabytes or even tens of gigabytes of data every minute and quickly overwhelm traditional computing resources that might be available within a laboratory setting. So the challenge here is that researchers now require access to equally advanced computing resources, whether that's HPC devices and supercomputers, GPU accelerated servers, or powerful specialized edge devices. However, the heterogeneity of these devices can cause issues in itself. Often they require time-consuming setup, knowledge of specialized software environments, and familiarity with HPC environments, and knowing how to actually tailor their workloads to these batch queues and specific request times and wall times can be an issue. We call this broad range of accessible computing and storage resources the computing continuum, and our goal is really to remove the barriers and enable researchers to perform tasks wherever it makes the most sense across this entire continuum. For example, some tasks could be performed wherever compute is readily available, others could be performed where the data is located, and others may be best suited to run at the edge or perhaps scale up on a supercomputer. So this work has long been the goal of many efforts, including grid computing and peer-to-peer computing. However, recent advancements in networking, containerization, and distributed trust fabrics really make it possible to reliably outsource these tasks across heterogeneous devices and expect that they can run in some timely manner. The diversity of computing resources in this continuum leads us to technologies to abstract the different devices such that we can enable people to use them. Serverless computing is a technique that really abstracts infrastructure from the user and allows them to focus on writing codes and executing them rather than worrying about what the computer is actually doing behind the scenes. Function as a service is a leading serverless technology. Function as a service allows users to define very small codes and then run them on demand. Pretty much every major cloud provider has some form of function as a service platform. And the way this works is that the user would generally pick a runtime, whether that's Python, JavaScript, or R, then write some code, a small Python function, and then run it at almost any scale. So the nice thing here is that the user doesn't need to worry about where that code is actually executing or having to provision the resources to run at a bigger scale. Instead, they just execute their code and it elastically scales behind the scenes. One nice thing about this is that you can actually tie these functions together to perform very complex tasks as well. So for example, I've got an image in the bottom right here, which shows Netflix and how it uses Amazon's Lambda to perform video encoding. Okay, this brings us to funcX. funcX is a function as a service platform designed to enable serverless science across the computing continuum. It lets you turn any machine into a function serving endpoint that you can reliably and securely send computations and run jobs. funcX removes the barriers to running on different machines as it abstracts the work to interface with underlying resources so you can deal with writing and running code. To use funcX, you have to first register a function with our service. You only need to register a function once and then you can run it on any accessible endpoint with some given input. You can also optionally associate a container with your function at the time of registering it. If you do associate a container, this will be used every time that you go to invoke the function. funcX relies on a very strict authentication and authorization model where we use globus auth. By default, functions can only be run by their owners. However, you can specify a globus group that you want the function to be associated with. And if you do this, any member of that group will be allowed to actually invoke the function. A funcX endpoint is a lightweight agent that you deploy on a device, and that does the work of abstracting the underlying resource so you can elastically scale up and down and fulfill tasks. So the funcX system comprises the funcX web service and endpoints. The web service provides a REST interface to register endpoints and functions and monitor their execution. Every interaction with the web service is secured with globus auth, so every function, endpoint, and invocation is associated with a specific user. This allows us to also enforce authentication and authorization and make sure users are only utilizing the functions and endpoints that they're actually allowed to use. At the center of a web service is a Redis store. This provides us a low latency mechanism to store functions, track tasks, and provide reliable input and output queues for each endpoint. behind the Redis store, we actually start a forwarder process for every single endpoint that is currently online. And this forwarder process is really responsible for taking jobs off the endpoint's task queue, routing them down to the endpoint, and then once results are ready or returned to the forwarder, it puts them back into a result queue such that users can come and retrieve those results from the web service. The endpoint agent is a process that is started on a compute resource and then receives tasks from its forwarder for execution. The endpoint securely connects out to its forwarder, so you don't actually need any special network permissions to be able to deploy this. And similarly, you can start it in user space, so you can deploy it on a login node of a supercomputer. We use 0MQ connections between the endpoint and the forwarder for low latency and reliable communication. And when the endpoint receives a task, it queues it internally until it can be dispatched to an available worker. The endpoint uses Parcel, which is a high-performance parallel scripting library, to interact with the underlying compute resources. This gives us a configurable pilot job model to actually deploy workers on different devices and reliably execute jobs there. To execute a job on an HPC center, for example, you would define a custom config file for your funcX endpoint that specifies which queue to actually use and the rate to scale up and down. The way this then works is the funcX endpoint will provision nodes on demand, and for each node it will deploy a manager on that node. The manager is then responsible for a pool of workers that will actually perform the functions as they're passed to it for execution. Users can modify the config of an endpoint to specify how it scales and what queues to use. And if there is a container associated with a function, the manager will actually deploy a worker inside that container to fulfill that job. Finally, the endpoint periodically replies to heartbeat messages to report statuses and usage information and show that it is still online. So when we put this all together, we have funcX, and it allows us to run functions on any endpoint that the user is authorized to access. I've got an example here from our tutorial notebook that shows how this actually works in practice. As you can see, we've got a funcX SDK. You can pip install this and start your own funcX client to actually interact with our system. In this example, we define a very simple summing function that will just sum a list of numbers and then return the result. In the third cell of the example, we actually use our funcX client to register this function. You can see that we actually pass in the pure Python function to be registered, and then behind the scenes in our SDK, we serialize and package that function and send it off to our service. The service then replies with a UUID for that function that you can then use to actually invoke it on demand. The fourth cell we use to actually invoke this function. So we define a list of input and then specify an endpoint to actually execute it on. In this case, we're using our public tutorial endpoint. This is a freely available endpoint that we operate on AWS. But you can replace that with the UUID of any endpoint that you have access to. You can pass any number of args or keyword args as input to the function. These are serialized by our SDK and packed into a buffer, then transmitted to our web service. And then the web service gets, or the input gets routed down to an available worker where it's deserialized and then acted on. Similarly, results are serialized by the worker and then returned back to the web service for access by the user. Alright, so what is funcX actually used for? We work with a number of collaborators around Argonne and the University of Chicago to sort of derive the requirements of this work and drive some of its capabilities. So here I've listed out 6 of our driving use cases, and I'll quickly go through them to explain sort of the capabilities that we can provide with funcX. Each of these use cases is instrumented with funcX to perform on-demand tasks with functions. The first one is the Xtract platform. Xtract is actually built on top of funcX and provides a way to do metadata extraction on demand. The nice thing about using funcX for Xtract is that it allows users to actually push these metadata extraction tasks out to data remotely, or apply a number of functions on the data once it's pulled to the Xtract service itself. DLHub is an on-demand machine learning inference platform. We've actually migrated DLHub over to use funcX for all of its inference requests. And the way this works is we've deployed a couple of funcX endpoints on different Kubernetes clusters to serve all of these machine learning models. funcX allows DLHub to dynamically scale up and down in response to load, so it will actually spawn more replicas of a specific model to serve incoming requests. The SSX, serial crystallography, and XPCS projects. These are two of our APS use cases at the Advanced Photon Source at Argonne. Really, these two both use funcX to outsource tasks to the Leadership Computing Facility, ALCF. This provides them a mechanism to actually use high throughput resources during their experiments and integrate their beamlines with the supercomputing capabilities that we have at Argonne. The neurocartography use case, this is one where we've actually exposed a library called Automo behind funcX, and this allows users to invoke tasks to create previews or perform full reconstructions on many gigabytes or terabytes of data using ALCF supercomputers. Finally, we've worked with our high energy physics group to create a funcX backend for the COFIA platform. This allows for parallel high energy physics analysis on columnar data. The way this works is it aggregates histograms of analysis products in near real time and can actually process over 300 million events in about 9 minutes using 2 different funcX endpoints. So this is a really nice example of a multi-site use case because the endpoints are deployed on 2 different machines and jobs can be fanned across both of them concurrently. The first question we normally get asked about this is how fast is it? So we've evaluated funcX's cold and warm start invocation time against Azure functions, Google Cloud functions, and Amazon's Lambda. To evaluate the warm start time, we've deployed functions in each provider's eastern region and then invoked them up to 10,000 times. To test the cold start time, we use the same functions and then invoke them 50 times with at least a 15-minute gap between each invocation. For funcX, we actually stop and start our endpoint, which we've deployed in the US East region of AWS on EC2, and we actually terminate and then restart this endpoint to ensure that our containers have to start from scratch to serve each request. As you can see, funcX performs fairly comparably with the others in terms of warm start latency. It's roughly equivalent to the others here. We sit about in the middle there with about 10 milliseconds on each side. However, the cold start time is much higher on average. This is primarily due to the instantiation time of the singularity containers we were using, and this cost goes away once the container is warm. In terms of scaling, we've deployed endpoints on Argonne's Theta and NERSC's Cori supercomputers. These endpoints are underpinned by Parcel, which is our highly performant parallel scripting library. Parcel enables our endpoints to scale to over 130,000 active workers, as shown here, where each worker is a distinct container as well. So this was achieved when executing 1.3 million no-op functions. On the right here, we've got our plots showing the strong and weak scaling. This is where strong scaling evaluates the performance when the total number of function invocations is fixed, and weak scaling evaluates the performance when the average number of functions executed on each container is fixed. So as you can see, it exhibits fairly good strong and weak scaling, and you can tell this by the fairly level strong scaling result and the steady growth of the weak scaling result as well. So they're not exploding out, which would be a bad sign. funcX endpoints are also elastic and capable of scaling up and down workers to meet demand. On the left here, we've got an example of a Kubernetes-based endpoint where managers are launched in response to load. In this case, we send 20 functions of specific duration and then monitor the workers that are started to serve those requests. On the top half of the plot, you can see the number of pending functions that are delivered to the endpoint, and on the bottom half, you can see the endpoints that are actually, the nodes that are actually acquired by that endpoint to fulfill the tasks. As tasks are completed, you can see that the endpoint releases the nodes back to the resource. On the right, we show fault tolerance of the endpoint, where we evaluate the latency of tasks submitted over time, and then either we terminate the manager on the top or we terminate the entire endpoint on the bottom. As you can see in the manager's case, 2 of the jobs are really impacted by this. This is because they were actually executing at the time, but the manager was lost, so they needed to be resubmitted. Following that, the average latency continues to grow until that manager recovers, and then we clear out the backlog. Down the bottom, you can see when we terminate an entire endpoint, so this means there are no available managers for work to be completed. This is quite impactful on the latency of these tasks until the endpoint recovers, and then we quickly clear through the backlog and can continue going. We also have a number of optimizations implemented in funcX. Here we show how worker prefetching and how batching tasks can improve the overall throughput of our endpoints. So on the left, we show worker prefetching. This allows us to configure how much work workers can actually request in a given time. and allow them to request more than they currently have capacity to actually compute. So this minimizes the number of requests that the worker has to do to ask for more jobs. When we increase this number, you can see that the overall completion time is reduced, and this is mostly important for very short duration tasks because it removes the overhead of the worker requesting more work. On the right, we have batching up the top. So this allows us to combine many individual requests into a single request that's sent through the web service. This really amortizes the cost of network latencies of transitioning through our service for many different requests. As you can see, this is really impactful again for short duration tasks like the MNIST example here, and it's a really effective mechanism to improve the overall throughput. Down the bottom, we've got user-driven batching. This is slightly different. This is using our map primitive, which allows users to submit an iterator as input to a function. And then the endpoint actually slices that iterator across a number of available workers. Using this approach, we've actually shown that we can achieve 1.2 million function invocations per second on a single AWS node, where we're using a C5N 9 times large instance. Finally, we've got container warming and memoization. So as I showed earlier with the latencies, starting new containers can be quite expensive. So we did a quick evaluation to work out what the cold start times were of these containers on different machines. So on Fader we were using Singularity, and on Corey we're using Shifter, and then on EC2 we tried Docker and Singularity. As you can see, it's fairly expensive to start a new container on the big supercomputers. We're not entirely sure what this cost is, but we're leaning towards it being contention of a shared file system. So we've got a bit more work to do here on how we actually optimize this cold start time. And below we've got memoization. So this is the case where we allow the endpoint to actually cache a result for a given function and input, and then if it gets the same request and it doesn't actually need to compute, it will return the result from the cache instead. This is mostly relevant to machine learning inference tasks where it can be sent the same request numerous times. So what have we actually learned from this? Firstly, our collaborators really liked how simple funcX made it to use heterogeneous resources. Being able to interact with different machines with the same interface was a really nice selling point of this work. They liked the simplicity of being able to automatically scale up and down, so that was quite nice. And they really enjoyed that they could use a single web-based authentication model to access many different machines. Because most of our work is really event-driven, responding to data being created and that sort of thing, we found that funcX was a really nice match for this, and it allowed us to opportunistically take advantage of computers with things like backfill queues, so that was quite useful as well. Our researchers really enjoyed the portability of funcX, and that it provided them capabilities to test things locally and then dispatch them off to a different machine when they wanted to scale up. And finally, they liked that they could share these functions between collaborators by creating and administering Globus groups that they could then invite other users into to access their functions. In saying that, funcX isn't exactly perfect for everything. So if there's a task with a lot of intercommunication, for example, large MPI jobs, we didn't find funcX to be extremely useful for that. We also found containerization wasn't necessarily the solution to all of our portability problems. So for example, the XPCS use case, we actually had to recompile their analysis code to run on different machines. Also, we found that it wasn't necessarily a perfect match for every use case that wanted to use on-demand computing with very low latencies if they were trying to use a large computer. So our supercomputers, even with backfill queues, they still don't fulfill jobs instantly. So we had to have maybe a minute or so's cold start time on some of these machines. And finally, decomposing apps wasn't always necessarily trivial. So for example, the neurocartography use case, we actually ended up packaging the entire library. In conclusion, funcX is a distributed, federated function-as-a-service system designed to meet the requirements of scientific computing. It enables computing almost anywhere in this computing continuum that I discussed earlier, and our endpoints are capable of scaling up to 130,000 concurrent workers, so we can scale to very large machines and also support laptops and local servers and that sort of thing. funcX is freely available on GitHub, so feel free to go and download it and start your own endpoints if you like. And finally, we've got our website available at funcx.org. Here we've got an example binder notebook that you can go and try out funcX without actually having to install anything. If you have any questions or comments, please feel free to email me or contact me on Slack. And yeah, thanks very much for listening.